Welcome, everyone. Course announcement, usual office hours times. Vincent will be tomorrow, Thursday at 10:30 a.m. Montreal time, and my office hours will be at 10 a.m. on Friday, as usual. Are there any questions? Baby goats are great. Okay, let's get started. We'll be doing more graph algorithms today, and then continuing in particular with max flow min cut next class. So let's start out with spanning trees. What is a spanning tree? So just to explain the context in which we're working here, we'll be working with undirected graphs. So an edge going from U to V is the same as that edge going from V to U. And weighted graphs. So there are weights associated with edges. A spanning tree in an undirected weighted graph is a subset of the edges that cover all the vertices of the graph and form a tree, i.e. no cycles. So here the shaded edges are forming a spanning tree. Spanning because it spans the entire graph. There are possibly many spanning trees in a single graph. Every connected graph has at least one spanning tree. And the way you can get to it is just by deleting edges one at a time, making sure you don't make the graph disconnected. So as long as you delete an edge that doesn't make the graph disconnected, you can gradually take out edges to find a spanning tree. How many edges does a spanning tree have? The number of vertices minus 1, exactly that number. And that's because the number of vertices in the spanning tree is just the number of vertices in the whole graph. And since it forms a tree, we know that the number of edges in the tree has to be one fewer than the number of vertices in the tree. We proved that earlier. So you take out edges, keeping the graph connected until you get to number of vertices minus 1 edges. And that is a way to get a spanning tree. Adding any new edge to a spanning tree must make it have a cycle. Why? If you add any edge to a graph, to a spanning tree, if you add any edge of the graph to the spanning tree, you get a cycle. Why? So for example, if I added this edge, I would form a cycle. If I added this edge, I would form a cycle here. And if I added this edge, I would, oops. Because it's a tree, that's the answer. Yeah, so we sort of showed that if you add an edge to a tree, you get a cycle, and that's because there's already a path, a unique path between any two vertices in the tree. So since it's connected, there is a path from here all the way to here, and if you add an edge, then there are now two paths from here to here. And they form a cycle. And since it's a spanning tree, you know that the tree covers all of the vertices of the graph. Okay, are there any questions? Okay. So what is a minimal spanning tree? So the weight of a spanning tree is the sum of the edge weights. This is like in shortest path, we're thinking of these edge weights sort of like lengths of edges, and we're thinking of the total size of a spanning tree is like the total number of the total lengths of all of those edges. And there's a problem finding the minimal spanning tree, or a minimal spanning tree, I guess I should say, in a weighted undirected graph that is connected. There might be several such trees with the same weight. There are some neat applications of this. It's a very broadly applicable problem, including designing circuits so that, you know, to do something most efficiently, if you need to connect up a bunch of vertices in a sort of electrical circuit, then the most efficient way to do it can be captured in minimal spanning tree. Building road networks if you need to connect up a lot of different cities, for example, in order to have the minimal amount of road to do that. Finding taxonomic trees is a cool example where the lengths correspond to like edit distances in DNA or other distance metrics, basically in evolutionary terms. We're trying to find the best taxonomic tree to represent the evolutionary branching between lots of different species, and you're trying to minimize sort of the evolutionary distance that was covered by the entire tree. So the number of like DNA mutations, for example, that happened in the course of the whole tree. Anyway, lots of different examples, and there's actually a biological situation where something very similar to minimal spanning tree is being solved by a creature called a slime mold. So a slime mold is a colonial amoeba, basically. It is a lot of individual cells that are separate, but they do things together. And one of the things that they do is they try to stay connected. So this is a really long, branchy slime mold. And there are these various places where there's food for it, these yellow spots. And the slime mold is trying to branch out and go feed from all the different sources of food while staying connected. And the way that it does this basically is minimal spanning tree. It's not exactly minimal spanning tree. It's actually a bit better than minimal spanning tree. It's more like a road network where there's a bit of redundancy. So here you can see this is a cycle. But actually, algorithmists have looked at this and they found that it does this solves this problem very efficiently. Questions at this point? Okay. So this is Prim's algorithm for finding a minimal spanning tree. Let's explore. If we start out at a vertex, let's say we're going to try to construct a minimal spanning tree, you know, starting at this vertex, branching out. What would be a natural choice for which vertex to choose next, or which edge to include next in the spanning tree? Yeah, and why would we choose that? The edge of minimal weight, which in this case would be B. Why would we pick that? Well, I mean, sort of a sort of greedy approach. We're like, well, probably we want to reduce the cost, so let's just pick the lowest weight. Okay. Now we have A and B and the edge between them in our spanning tree. What do we do now? And yes, this does feel a bit like Dijkstra. There's a reason I put these two together. So what do we do next? In some sense, this is simpler than Dijkstra. So there's a suggestion of the minimum weight. What minimum weight exactly? Like, should we pick the minimum weight coming from B? We just added B. Should we pick the minimum weight edge coming from B? So we can pick the minimal weight to a new vertex. We definitely want to add a new vertex. If we circled back to an existing vertex, we'd be in trouble. We only have 2 vertices here. So we could pick the minimal weight coming from B, but we could also just say pick the minimal weight edge coming from any, either of A and B. In this case, that's actually a tie. You could pick this one or this one. Both of them have weight 8. Let's pick this edge. So we add this edge. And then we can do the same thing. We can say at each step, we're going to look at all the edges leaving the set of vertices we already have, A, B, C in this case. And we're going to pick the one with minimal weight. So here there's an edge out of this set, from the set of vertices we have to the set of vertices we don't have. And the minimal weight one is this edge of weight 2. Okay. And then we can keep on doing this. We can say, what's the next one? Well, the next one's actually 4. We branch out here. The next one, if you look at all the edges from these vertices, A, B, C, F, I, to the vertices that aren't in our set, D, E, G, H, the minimal weight one is 2. And then we keep on going. And I guess we would then add 1, and then we would add 7, and then we would add 9. And so that is the algorithm for finding a minimal spanning tree. Or this is Prim's algorithm, one of the algorithms for finding a minimal spanning tree. But we haven't showed why it works. This is sort of intuitively a way that this is a reasonable thought. Maybe if you go sort of greedily trying to do this, you would actually get to an answer. And again, we're growing a subtree, Ti, one vertex at a time. This is the subtree. At step I, we consider edges from the vertices we already have to new vertices. So here we're considering all the edges from these 4 vertices to the other 5 vertices. And we take the edge with lowest weight, which in this case would be the edge from C to F. We add that edge and the new vertex to get a new tree, Ti plus 1. And then we stop and we have no more vertices to add. Are there any questions about the algorithm itself? This is easier than Dijkstra's algorithm because we don't have to like update these guesses of distances and stuff. But it still has some flavor because we're sort of taking we're taking a minimum in order to decide where to go next. Are there any questions? Okay, so let's try to prove that this is correct. First of all, how do we know that this gives us a spanning tree? Go back to the, well, no, I'll leave it here. How do we know that this gives us a spanning tree? Remember, there are 2 things that have to be true if it's a spanning tree. It has to have all of the vertices, and it has to be a tree. Why are those 2 properties true? Yeah, so we add a new edge only if the vertex is new too. So we never end up with any cycles. It means it's a tree. Remember, we're adding a vertex from which we're adding an edge only if it goes from the vertices we have to a new vertex. So we can never cycle back. And it's spanning because it has all the vertices, because we stop only when we have all the vertices. And we can get all the vertices because it's connected. So if we ever had a set of vertices where we could not get to the other set, then we would have a disconnected graph. Okay. Why is it minimal weight? And what proof technique might we want to use in this case? There are different ways to do this. There's a lot of suggestions of contradiction, and we will end up using contradiction. I'm going to actually wrap it in an induction step. But in a lot of cases in these kinds of algorithms, we're going to basically be doing induction and contradiction. And either we do a contradiction and then an induction, or an induction and then a contradiction. And I'm sure you could do it the other way here. But so we're like, let's first wrap it in an induction, and then within that, we'll end up using contradiction. So the inductive hypothesis is going to be that at each step, the tree that we have, Ti, is a subset of a minimal spanning tree for G. Why is this enough? If we prove that this induction works, why would this be enough to solve the problem for us? If we could prove that this induction works. Don't overthink this. Again, I'm just asking, if we could prove that this holds for every I, why would it prove the problem? We're doing an induction on I here, on the size of the tree. We're not changing the size of the graph, to clarify. So we start out with a graph of, the induction is going on a graph of fixed size. And we say, okay, well, when we start out with a subset of a minimal spanning tree. And then at each step, we are continuing to stay within a minimal spanning tree. And then at the end, we have an entire spanning tree. And then at the end, if this inductive hypothesis is still true, then we have a spanning tree, which is a subset of the minimal spanning tree, which means that the final thing that we have is the minimal spanning tree. Does that make sense? So again, we're just doing an induction on the steps that we're performing within the algorithm. We're not doing an induction on the graph itself, on the ambient graph that we're inside. Okay. So what's the base case? Why is the base case easy here? What is the base case? Yeah, never pick a base case that is more complex than you need. We could pick a base case that's the smallest edge, but we could just pick a base case which is one vertex. We start out at one vertex. That is our base case, like T0. The base case of one vertex is easy because every vertex is clearly a subset of the minimal spanning tree, of any minimal spanning tree, because the minimal spanning tree has to include every vertex. Very simple. Okay. Now suppose that it's true for T sub k. So it's a subset of a minimal spanning tree M. That's our inductive hypothesis. And now suppose we get to tk plus 1 by adding the edge e. So if e is an m, then we're done. Because we're still inside the minimal spanning tree. This is where it basically is a contradiction. So suppose e is not an m. What is true then? So we're basically, there is this spanning, minimal spanning tree M, and we found a part of it, and then instead of adding an edge to the other part, we find a different edge. Actually, share my screen like this. Can you see? Okay. So here we have our tree TK. And here, it's part of a bigger tree. M. Oops. And instead, oops, so this is the set of vertices we haven't visited yet. Oops, sorry. This is the set of vertices we haven't visited yet, I should say. So instead of adding one of these edges, we add another edge. We add the edge like this. What is true here? I'll say we add this edge. Easier. What do we know is the case? We're going to get a cycle. There is this cycle here. Okay. Cool. Why does that help us? It makes it not a tree. But I mean, it's we don't actually have M. M is sort of the hypothetical minimal spanning tree that we want to stay inside of. But at the moment we've added a bad edge. We should have added maybe this edge. Make this a little bit clearer. We should have added, oops. We should have added, let's say this edge here. But we didn't. So we have a cycle. The edge that we did add, let's call it E. In this cycle, there's going to be some edge, E prime, which leaves TK. And so E prime is in M, but it's not in It's not in TK. What is true about E prime and E? Remember, we picked E to add to TK. Why did we pick E? What was our algorithm for picking E? Which one of them has smaller weight? There's some disagreement. E has to have smaller weight. The weight of E is less than or equal to the weight of E prime, and that's just because we decided to add E instead of E prime. There might have been a tie. Okay. So what can we do? Remember, this is a contradiction now. We're trying to find a contradiction. We said we added E, but we should have actually added E prime, which would have stayed within the minimal spanning tree. But the reason we didn't add E prime is because the weight of E was less than or equal to the weight of E prime. So the suggestion that we'd like to violate our assumption that M is a minimal spanning tree. How can we show that M is not a minimal spanning tree? How could we prove that in fact our minimal spanning tree M was not a minimal spanning tree? Yeah, we could take out E prime and we could add in E. That's a spanning tree because we took out an edge from a cycle, and so it still has to be connected and it still has to cover all the vertices. So it's a spanning tree. And why is it better than M? Well, it's not necessarily better than M, but we do have the weight of M prime now, if our new thing is M prime, is less than or equal to the weight of M because of this thing. Since we have that the weight of E is less than or equal to the weight of E prime, we just changed out E prime and E. So the weight of M prime is less than or equal to the weight of M. And that's all we need, because our inductive hypothesis, remember, was that we are at every point we have a subset of a minimal spanning tree. Didn't say we were a subset of the only minimal spanning tree. There might be several minimal spanning trees. Are there any questions about this? I'm going to go back to the slide in a moment. Can you still see the slide? No, okay. There. You should be able to see the slide now. Cool. So if E is an M, then we're done. Otherwise, let's think about adding E to M and just summarizing what we did in the whiteboard. This has to make a cycle since M is a spanning tree. Now there's some other edge, E prime, in the cycle that we could have added instead of E. It's an edge from the old vertices in TK to the new vertices outside of TK. since we didn't add it, its weight must have been bigger or equal to the weight of E. And so we can swap out E and E prime in the spanning tree M, and that gives us a new spanning tree M prime. And the weight of M prime, since we swapped out E prime and E prime had a greater than a weight that was greater than or equal to that of E, we must have the weight of M prime be less than or equal to the weight of M. I mean, I guess it's not really a contradiction. I'm sorry, I probably shouldn't have written that it's a contradiction. It's just saying it's not a full contradiction. So if it's less than the weight of M, then it is a contradiction. But since M is just one minimal spanning tree, it's possible that M prime is just another minimal spanning tree. And I guess I should have said either M prime is just another minimal spanning tree, in which case the inductive hypothesis holds, or we have a contradiction. Questions? So it's not really quite a contradiction proof. It's almost a contradiction proof. Okay, let's go on. So again, here's the algorithm. We add the minimal edge from the vertices we've already added to the new vertices. Here we add 4, here we add 8, and 2, and so on. How can we implement this? What's a good way to implement this fast so that we can have a pretty low running time? What is a data structure that we can use, bearing in mind that we basically covered no data structures, to help us do this efficiently? The suggestion of priority queue. What should be in the priority queue? What are the objects that we're storing in the priority queue? Like, how large is it? Again, we're adding a vertex and an edge one by one, based upon whichever edge is smallest from the vertices we have added to the vertices we haven't added. So we could store all the edges. But then we'd have to keep on adding new edges because the edges that we're considering adding are only the ones that are incident to the vertices we've already had. So we'd have to keep adding and taking away. And adding things is sort of hard to a priority queue. We want to just take things out of the priority queue. We don't want to ever have to put things back in. We could have the vertices in the priority queue. So we could keep a minimum priority queue of vertices we haven't added. And so every time we add a new vertex, we just take it out of the queue. Then again, we have a queue, great, but what is the key for each vertex? Like what is the thing we're applying the min to? Yeah, there was a suggestion. I mean, basically we want to always have, if we're doing a min priority queue, we want the min operation to be the thing we're using. So in this case, we're finding the vertex which is closest to the vertices we already have. So we can have the key be the distance to the vertices we already have. But so we don't have to compute distances. We could just have it be the minimal edge. So here, if we have no minimal edge, we can have just distance. We can say that they're infinity. The key is infinity. And going back here, we say, okay, well, going from this step to this step, we had a priority queue of all these things, and this had no edges to A or B, so its key was infinity. But this one had 8 as its key, and this one actually also had 8 because there were 2 possible edges, but the minimum one is 8. Here, so we could have taken either of those from the priority queue, and it depends upon how the priority queue was implemented, which one of those was actually at the top of the priority queue. Now here, we would have a single possibility for the top of the priority queue, which is this, which has only actually 1 edge going in, which is 2. Here, there were 2 edges going in. There were 8 and 11, but the key in the priority queue would be the minimum one, which is 8. And notice that at each step, we're adding something new to the priority queue. So here, for example, we add a new vertex. Sorry, we add something new to the vertices we have. So we take something out of the priority queue. Here, we remove I from the priority queue. And we suddenly have some new edges to consider. We have to consider this edge and this edge. This vertex, H, suddenly got closer because we now have an edge of length 7, and previously there was an edge of length 8. That was the minimum edge. So now the minimum has gone down for this vertex, and the minimum has gone down for this vertex too. Previously, this vertex was infinity as the key, and now it's 6 as the key. Okay. Are there questions about this? The new vertex to add, we're just doing extract min. We're finding the vertex that has the minimum edge. And when we add a new vertex, we just do decrease key on any neighbors that are now closer. When we add a new vertex, we check all of the neighbors. We check all the things that it has edges to. And some of those will decrease the key. Some of them won't because the edges are long. But yeah. How long does this take if we use a min binary heap as a min priority queue? So the implementation of a priority queue that we were using before. Any guesses about how long it takes? How long does it take to make the queue in the first place? Time complexity worst case. How long does it take to make a heap? So making a heap is going to take O of n, linear time and the number of vertices, which are the things in the heap. How long is it going to take to do all the extract mins? Remember, extract min is different from just min. Extract min is take out the min. Remove it from the priority queue, and then you have to rearrange the priority queue. So each one of them is going to take log v time, or a big O of log v time. It might take less, and the final ones are going to take less time because there aren't v vertices in the queue. But you're going to have O of v calls to extract min, and each one of them is O of log v. What about decrease key? How long does it take overall? That includes how long each one of them takes and how many times you call it. A couple of suggestions. Each one of the decrease key operations takes big O of log v. And the number of calls is actually going to be big O of e, the number of edges. The reason for that is that we're doing it for every one of the edges coming out of this vertex. Or we might do it, possibly, for every one of the edges coming out of the vertex. And that means that we're considering each edge in the graph once. And so the total number of calls to decrease key is upper bounded not by the number of vertices, but by the number of edges. So overall, we're going to get v times log v plus e times log v. Sorry, I guess I should be saying cardinality of v plus log of cardinality of v. And again, number of edges is at least the number of vertices minus 1, so this just becomes big O of e log v. Are there questions about this? As with Dijkstra, there is a faster implementation, which can actually be done in v log v plus e time. Big O of v log v plus e. That is faster in some cases. If the number of edges is just order of v, then it's not any faster, but it's not any slower. And this is, again, using Fibonacci heaps, which we haven't talked about yet. OK. So let's move on to flow networks. We're going to start on max flow, but we're not going to get very far this time. We'll finish it up next time. So we've seen some problems, shortest paths and spanning trees, where the weights on the edges in a graph are basically used to represent lengths. So we think of them sort of as lengths, and the overall weight of something is like the sum of those lengths, basically. It's like a cost. You can also represent the maximum capacity on edges with weights. Sort of intuitively thinking of them as a max capacity. So a flow network is a directed graph where for every edge uv, there's an associated capacity, which is basically a weighted graph. It's a directed weighted graph, essentially. But the weights are called capacities, and they're denoted C of uv. And if you have an edge, then the capacity on that edge is going to be greater than 0. I'm going to assume that there are no self loops, just for the sake of, for simplicity. So a flow in a flow network from S to T, S is thought of as a source, T is thought of as a sink, is a function, F, where if UV is an edge, then the flow, F of UV, is less than or equal to the capacity on that edge. And in particular, if there's, it's also defined if there's no edge, and the flow is just 0 if there isn't an edge. And where for any u that are different from S and T, that aren't the source of the sink, the total flow going out of the vertex, sum of f of v u for all v, this is all the flow going into the vertex. The sum of f v u for all v, total flow going in, is equal to the total flow going out, sum of f u v. So here is an example. This is a flow network where there are no self-loops. Each of these edges has a weight, and that's the capacity. And here we're denoting the amount of flow and the capacity together. So this is not 11/16. It's a little bit of a weird notation, but it's basically saying that 11 is the amount of flow. So 11 is F, and 16 is C. So it's 11 out of 16. And the reason why sort of to write it like this is basically saying like there was 16 possible, but we're taking 11. So here we have, for every vertex that is different from S and T, we have this sort of conservation of flow. The amount of flow going in is the same as the amount of flow going out. So here we have 11 and 1 flow going into this vertex, and 12 flow going out. So 11 plus 1 is 12, so that's good. Likewise here at V2, we have 4 going in, and we also have 8 going in. And we have 1 going out, and we have 11 going out. So here is, again, 12 going in and 12 going out of this vertex. And here we have 11 going into this vertex and 11 going out of the vertex. But for S, we actually have 19 going out. And we have, for T, 19 going in. So it doesn't have to be, the flow doesn't have to be conserved at S and T. It has to be conserved everywhere else. And again, all of these flows have to be bounded from above by the capacity on that edge. And if there isn't an edge, then you can't do flow. And also, you can't do flow in the wrong direction. So you couldn't take the flow along this edge because it's pointed this direction. You can only take flow from V3 to V2. You can't take flow from V2 to V3. But you could have two edges going, one from V3 to V2 and one from V2 to V3. And if you had that kind of graph, then you could do flow in both directions. Are there questions about these definitions? Okay. So again, this is the definition of flow. We say that the value of a flow is just the amount going out of the source minus the amount going into the source. In this case, there's nothing going into the source. So here, the amount going out of the source, the value of the flow is just 11 plus 8, the amount going out, which is 19. Now we noticed that the amount going out of the source seems to be equal to the amount going into the sink. Why is that true? How can we prove that? Any thoughts? Intuitively, why is it the case? If we're thinking about this like flow of like electricity or flow of water, you think that flow has to be conserved. So we sort of imagine that if it's coming out of somewhere, then it has to go into somewhere. And so let's make this formal. Here's a way to make it formal. If we write this thing for summing over all u and v, clearly this has to be equal to 0. That's because we're summing f of uv, and we're also summing f of vu. And since we could interchange v and u, if we interchange, because we're now summing over both u and v, we are adding each edge's flow, and we're subtracting it. So this has to all cancel. Okay, we can write out this sum as the sum if u is s, the sum if u is t, and the sum if u is anything other than s and t. Now we know that this is equal to the amount of the flow, the value of the flow. And this is the thing we're trying to work out, the amount flowing into or out of t. And this, because we have conservation of flow, we know that for any vertex that isn't the source of the sink, the amount going in has to be the amount going out. And so this is 0. So here we end up, this is 0 equals 0 plus the value of the flow plus this thing we're trying to work out. Because the thing we're trying to work out is the negative of the value of the flow. And if you just swap it, we see that the amount going into f minus the amount going, the amount going into t minus the amount going out of t is going to be equal to f, which is just what we're going to just show. We will continue with flow in the next class. I will stick around for a few minutes for questions. Thank you everyone for coming, and here is a poll about the speed of class.